Good morning everyone. My name is Jay Harshit, CSC B section 21980 PPT on applied physics. My topic is quantum switching and quantum merging. Merge sorting. Abstract. This paper proposes a quantum switching architecture that can dynamically permute each input quantum data to its destination port to avoid using the fully connected wire networks. In addition, in order to reduce the execution time of the quantum switching, an efficient quantum merging source sorting algorithm that provides a parallel quantum computation is also developed. This quantum switching utilizes the QMS algorithm as a subroutine so that the total running time can be reduced to polyalgorithmic time. Furthermore, to evaluate the feasibility of quantum switching, we also defined three different kinds of performance factors that can be used to estimate the complexity in implementation and the time delay in execution for quantum instruments. From the evaluation results, it can be seen that proper quantum switching is feasible in practice. Quantum computation and quantum information science that study the exploration of quantum mechanics provides us advanced tools to solve difficult problems in traditional using machines. The fundamental elements in the quantum field can be any particle with two states that coexist together, such as photon, atom, electron, subatomic particle. All of them are under the nanoscale. Thus, QoS is often considered to be a basic for further research and innovations in the future development of nanotechnology. In literary, many outstanding algorithms have been developed to illustrate that quantum based computers are more powerful than traditional computers. For example, Sure presents a quantum algorithm that factors a composition integer exponentially faster than the best classic algorithms do, and Groove presents a quantum algorithm that searches an item from an unstructured list polynomial speed up over classical algorithms due to its potential impact and significance. QoS has drawn more and more attention in recent decades. One of the most important applications in QoS is the quantum communication, that is, a mechanism for transferring quantum data from one location to another. Among them, quantum wire is one of such mediums for transporting quantum information at present. Many remarkable research issues based upon the quantum wire configuration, such as quantum teleportation, quantum cryptography, quantum repeater, and quantum networks, have been raised. These results have driven the QoS field further into real world applications. Many views of the future of QoS indicate that the need for basic quantum wire components would become more essential due to explosive growth of quantum devices. As shown in figure, in order to ensure that Any two quantum devices can communicate quantum data with each other. It is necessary to employ a quantum wire between them. However, this results in a fully connection quantum network that would raise n squared quantum wires to construct, where n is the total number of quantum nodes. In this paper, a novel quantum switching architecture is proposed to avoid the fully connected quantum networks. As shown in the figure, with the aid of quantum switching, quantum nodes only need to deliver their quantum data to the quantum switching, and the quantum switching would switch it to its destination port. Thus, each quantum node only requires one quantum wire to connect with quantum switching. So the number of quantum wires can be reduced to ON. Quantum network architecture, fully connected quantum switching. The proposed quantum switching allows each input quantum data to be permitted to its corresponding destination port in parallel dynamically. Moreover, to maintain the time delay in executing the quantum switching and efficient quantum merge sorting algorithm is developed in this paper. Although it has been shown that quantum computers in general cannot greatly outperform classic computers for the tasking of sorting, this paper makes out of the parallel computation technique to reduce the running time of the QMS algorithm, so that it only takes time complexity to sort quantum elements. Because the purposed quantum switching utilizes the efficient QMS, the total execution time can be reduced to Polymerase algorithmic time. In addition, in other two axes, the feasibility of quantum switching, we also define three different performances indexes to evaluate the efficiency of quantum instruments. According to the results, it can be seen that the proposed quantum switching is feasible to put into practice. This paper represents one of the few attempts to solve the dynamic quantum switching in the literature. The remainder of this paper is organized as follows. In section, the general concepts about quantum computation are introduced. Related research is surveyed as well in section 3, the quantum vacuum system algorithm that provides a parallel quantum computation is presented. In section 4, the quantum switching architecture, its purpose to switch quantum data to its corresponding port. Finally, conclusions are drawn in section 5. Background and related work. Quantum states classified the underlying units in QIS is a quantum bit. However, unlike a classic bit that must be in state either 1 or 0, A qubit can be in both state and state at the same time. This special phenomenon in quantum computing is called superposition. In general, a qubit state is often represented as a linear combination of these two states. As shown in the diagram, this is the formula of quantum states, where alpha and beta are complex numbers and alpha square plus beta square equal to 1. Note that is impossible for us to determine whether a quantum bit Note that it is impossible for us to determine whether a qubit is in state by examination the values of alpha and beta. However, when we measure a qubit in a superposition state, the entire qubit system would collapse into one of its bases, as per which state we would obtain it is determined by the absolute square of its coefficient. That is, we get the qubit in state with probability alpha square or in state with probability beta square. Thus, alpha and beta are called probability amplitudes. Furthermore, a multiple qubit system can be built up by composing multiple independent qubits. To compose two or more qubit systems together, the tension product operator is adopted. For example, consider a two-bit system composed of two single-slit qubit systems, rho equal to A0 plus B1 and rho equal phi equal to C0 plus D1. Then the entire qubit system is usually represented as rho into phi equal to rho pi equal to AC00 plus AD01 plus BC10 plus BD11. Quantum unitary gates. In digital information processing, a basic circuit combined with some fundamental logic operators so as to complete a specific task is called a logic gate, such as the classic NOT gate, AND gate, or gate XOR gate, and so on. Analogously, in the quantum realm, a set of operators that can be multiple at a quantum system to accomplish a specific computation is called quantum gate. In this section, we introduce 4 quantum gates that are in common use throughout this paper. Similar to the classical NOT gate, the quantum NOT gate applied on a single qubit can be used to flip its states. Zero and 1 as shown in. Besides, the quantum NOT gate is usually called as a tuple X gate. The circuits of control NOT gate for processing 2. These are the diagrams of quantum NOT gate, C NOT gate, swap gate, and control swap gate. Take a look and we'll move to the further section. Qubits. It can be seen from that the quantum C NOT gate has two inputs. One is control qubit and the other is the target qubit. when the control qubit is set to C0 and gate does not nothing. On the other hand, if the control qubit is set to 1, then it would apply the NOT gate to target qubit. In other words, the C0 gate can be used to exchange 10 and 11. Besides, one more important quantum operator is the quantum swap gate. The swap gate applied on a 2-qubit system can be used to the transposition. More precisely, it changes a 2-qubit system from as drawn in figure. This swap gate can be implemented by 3 layers of C0 gates. However, because of its importance to quantum communication, swap gate is often seen as a basic quantum gate. The last quantum operator we introduce in this subsection is the control swap gate. As described in the control swap gate has 3 input qubits A, B and C. The qubit C is called a control qubit because it controls the happens in the 2 qubits. When the control qubit C is set to 0, it does nothing. On the other hand, if the control qubit C is set in 1, then the swap gate is applied to the target qubits. In quantum circuits, time evolution goes from left to right. Furthermore, each quantum operation is defined to be certainly reversible, so it can be done in principle without consuming any energy. This particular reversibility property is also put to use by proposed quantum switching so as to clean up some garbage bits. Quantum digital switch. In literary, psi and Q present a digital switching that can switch digital data in quantum domain. The basic idea of that digital switching is to apply the property that any general cycle can be performed by using 6 layers of C0 gates. This results in the digital switching being able to be implemented in a constant time complexity. However, the control module in their digital switching was absent. The control module is responsible for controlling the switching configuration so that all of the input data is each individual that can be switching to their destination ports correctly in the order to dynamically control the switching modules in each. In addition, Shukla et al. Present a quantum Banyan network that only requires logarithmic execution time to switch input data. However, the quantum Banyan network is not revertible since it needs to discard some dummy packets. In addition, the most serious problem in quantum Banyan network is that some input quantum information would be lost. Further, in the worst case, it is possible for quantum Banyan network to lose input quantum packets, varies the total number of input packets. According to no cloning theorem, these lost quantum data cannot be recovered. This would result in an unrealizable quantum network. The proposed quantum switching can overcome these drawbacks. The quantum switching is designed to be reversible. Moreover, input data would be lost in executing quantum switching. The quantum operations for implementing the quantum switch are described clearly in section 4. Since the quantum switching is constructed by applying an efficient quantum sorting algorithm, we briefly discuss some of the existing quantum sorts. Thank you.